Right now, you are moving. You don't feel it. You're sitting or lying down or standing still. But you are moving. The ground beneath your feet is rotating at about 1,000 miles per hour. The planet itself is orbiting the sun at roughly 67,000 miles per hour. The entire solar system is sweeping through the Milky Way at about 500,000 miles per hour. And the Milky Way, our galaxy, our home, is hurtling through space toward a gravitational anomaly we call the Great Attractor at over 1 million miles per hour. You have never been still, not once in your life. This is where we begin, not with the distant and the abstract, but with you here now, already embedded in the motion of the cosmos. Because the universe is not something out there, behind glass, in a museum. It is a thing you are inside of. It is a medium in which everything you have ever known exists. So let's take a moment to understand where exactly here is. You are on Earth, a rocky planet, roughly 8,000 miles across, orbiting an average-sized star we call the Sun. The Sun is not special in any cosmic sense. It is one of somewhere between 200 billion and 400 billion stars in our galaxy. And our galaxy is not special either. It is one of roughly 2 trillion galaxies in the observable universe. Let that number sit for a moment. 2 trillion galaxies. The Milky Way itself is a barred spiral galaxy, a flat, rotating disk of stars, gas, dust, and dark matter, with long arms curling outward from a central bar. If you could look at it from above, it would resemble a slow, luminous pinwheel. From edge to edge, it stretches roughly 100,000 light years. A light year is the distance light travels in 1 year. Light moves at about 186,000 miles per second, roughly 6 trillion miles per year. So when we say the Milky Way is 100,000 light years across, we mean that if you could somehow travel at the speed of light, the fastest speed permitted by the laws of physics as we understand them, it would still take you 100,000 years to cross it from one side to the other. Our solar system sits roughly 26,000 light years from the galactic center, about halfway out along one of the Milky Way's spiral arms, a somewhat quiet, unremarkable region of the galaxy. There is nothing particularly significant about our location. We are not at the center. We are not at the edge. We are in what astronomers sometimes casually call the suburbs. And here is the first philosophical note worth pausing on. The fact that we are unremarkable in position is not a diminishment. It is a liberation. Every time science has moved us away from presumed center, first the Earth, then the solar system, then the galaxy, what is given back in return is scale. It has replaced a small, special world with an incomprehensibly vast, democratic one. Every point in the cosmos is, in its own way, equally peripheral, equally ordinary, and equally extraordinary. Now, the Milky Way does not exist alone. It belongs to a group of galaxies, the local group, which contains around 80 galaxies in total, with 2 large spiral galaxies dominating. Our Milky Way and the Andromeda Galaxy, about 2.5 million light years away. In the night sky, if you are far from city lights, you can see Andromeda with the naked eye. It appears as a faint smudge, and yet it is the most distant object visible to the unaided human eye, 2.5 million light years away. The light entering your eye left that galaxy roughly 2.5 million years ago, when our ancestors were stone tool-making hominids walking across the African savanna. That's not poetry. That's physics. The local group itself is part of an even larger structure, the Virgo supercluster, which spans about 110 million light years and contains more than 100 galaxy groups and clusters. And even the Virgo supercluster is just one lobe of a titanic cosmic structure discovered in 2014, which astronomers named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster complex stretching 500 million light years across, containing the mass of roughly 100 million billion suns, and home to more than 100,000 galaxies. Our Milky Way is somewhere in the outskirts of Laniakea. And Laniakea itself? It is one of millions of similar structures scattered throughout the observable universe, connected by vast filaments of dark matter and gas, a cosmic web, a skeleton of the universe. with enormous voids of near emptiness stretching between them. This is the architecture of the cosmos. Not chaos, not uniformity. A web. Now we arrive at the real question. How big is all of this? And the honest answer, the scientifically honest answer, is that we have to be very careful about what we mean when we say the universe. Because there are, in fact, two different things we might mean by that word: the observable universe and the universe as a whole. These are not the same thing, and confusing them is one of the most common mistakes in popular discussions of cosmology. Let's start with what we know. The observable universe is not a philosophical concept. It is a physical limit defined by the speed of light and the age of the cosmos. The universe is approximately 13.8 billion years old, 13.787 billion years, with a margin of uncertainty of about 20 million years. That age comes from multiple independent measurements, including detailed observations of the cosmic microwave background, the oldest light in the universe. Because light travels at a finite speed, there is a maximum distance for which light could have reached us since the universe began. Any object beyond that distance, no matter how real, no matter how massive, is simply invisible to us, not because we lack the technology, but because the light from that object hasn't had enough time to reach us yet. This boundary, this edge of what we can, even in principle, observe, is called the cosmological horizon, or sometimes the particle horizon. Now here is where it gets counterintuitive. You might think the universe is 13.8 billion years old, so the farthest we can see is 13.8 billion light years in any direction. That would be the logical conclusion, but it is wrong. Here is why. The universe has been expanding since the Big Bang. Space itself is stretching. The galaxies we see at great distances are not sitting still while their light travels toward us. The space between us and them has been growing the entire time that light was in transit. So by the time the light from a very distant galaxy finally arrives at Earth, that galaxy is no longer where it appeared to be when the light left it. It is much, much farther away. The result is this. The radius of the observable universe is not 13.8 billion light years. It is approximately 46.5 billion light years. The full diameter from one horizon to the opposite is about 93 billion light years. A sphere of 93 billion light years across. That is the observable universe. Think about what that means. The universe is 13.8 billion years old, and yet the observable universe is 93 billion light years wide. Space has been expanding faster than light can cross it, and this is not a violation of Einstein's theory of relativity. Nothing is moving through space faster than light. Space itself is expanding, and there is no speed limit on expansion of space. The galaxies are not speeding away from us. The space between us and them is simply growing. There is an important boundary worth understanding here, called the Hubble radius. At a distance of roughly 14 billion light years, the expansion of space is so fast that a point at that distance is receding from us at exactly the speed of light. Beyond that distance, points in space are receding faster than light. This means that light emitted today from beyond the Hubble radius will never reach us. Not because it moves too slowly through space, but because the space it needs to cross is growing faster than it can traverse it. The light we see from the most distant regions of the observable universe, light from close to the beginning of time, was emitted when those regions were much closer to us. That light has been traveling for 13.8 billion years. But the regions that emitted it are now roughly 46 billion light years away, because space has expanded so dramatically in the intervening time. The farthest thing we can detect with our current instruments is not a galaxy. It is something called the cosmic microwave background, the CMB. This is not a galaxy or a star or any discrete object. It is a glow, a faint, nearly uniform radiation that fills the entire sky in every direction, a relic of the early universe. About 380,000 years after Big Bang, a period sometimes called recombination, the universe had cooled enough for protons and electrons to combine into the first neutral hydrogen atoms. Before this moment, the universe was a hot, dense plasma, opaque to light. Photons could not travel freely. They were constantly absorbed and re-emitted. When recombination happened, the universe became transparent. The photons that had been trapped in this plasma were suddenly free to travel, and they have been traveling ever since. Those photons are what we detect as the cosmic microwave background. The CMB is, in a very real sense, a photograph of the universe at 380,000 years of age. A photograph taken from every direction simultaneously. And it represents the farthest back in time and the farthest distance from which any electromagnetic signal can have reached us. It is our observational wall. Beyond it, in the first 380,000 years of the universe's history, the cosmos was opaque. We cannot see through it with light. Now, how much is inside this sphere of 93 billion light years? Current estimates suggest there are several hundred billion galaxies in the observable universe. A 2016 study led by Christopher Consolis at the University of Nottingham proposed as many as 2 trillion, but that figure was revised downward in 2021 using data from NASA's New Horizons spacecraft, which measured background light levels from beyond the solar system and found insufficient light to account for 2 trillion galaxies. The current working estimate is in the hundreds of billions. That number, 2 trillion, was revised upward dramatically in 2016 when a team led by Christopher Consolis at the University of Nottingham used deep field imaging and new mathematical models to determine that previous estimates of roughly 200 billion galaxies were at least 10 times too low. The vast majority of those 2 trillion galaxies are simply too faint and too distant for our current instruments to image directly. Each of those galaxies contains, on average, hundreds of billions of stars. The Milky Way alone has perhaps 300 billion. Some galaxies have trillions. The number of stars in the observable universe exceeds the number of grains of sand on every beach and every desert on Earth by orders of magnitude. This is not a metaphor intended to impress. It is simply the output of the math when you take 2 trillion galaxies and multiply by an average stellar population. And nearly all of the matter we can detect, is made of what physicists call baryonic matter. Protons, neutrons, electrons, the ordinary stuff of atoms. But here is something that should give you pause. Ordinary matter, the atoms, the stars, the planets, everything you have ever touched or seen or measured, makes up only approximately 4.9% of the total energy content of the universe. The rest is dark matter, roughly 26.8%, and dark energy, approximately 68.3%. Dark matter is something that exerts gravitational influence. We see its effects in the rotation of galaxies, in the bending of light around galaxy clusters, in the large-scale structure of the cosmic web. But we do not know what it is made of. We have not detected a dark matter particle directly. It is called dark not because it is sinister, but simply because it does not interact with light. It neither emits nor absorbs electromagnetic radiation. Dark energy is even more mysterious. It is the name we give to whatever is causing the expansion of the universe to accelerate. A discovery made in 1998 that surprised almost everyone in cosmology. We don't know what dark energy is. We don't know why it has the value it does. We can measure its effects with considerable precision, but its fundamental nature remains one of the deepest open questions in all of science. So here's the honest picture of the observable universe. A sphere approximately 93 billion light years in diameter, containing at least 2 trillion galaxies and hundreds of sextillions of stars, with 4.9% of its energy content being the matter we understand, and the remaining 95% being things we have names for but cannot yet explain. This is not a failure of science. This is science at work, precisely, honestly, and with the humility to say, we know the shape of what we don't know. And there is one more thing worth understanding before we move on. When you look up at the night sky, you are not seeing the universe as it is. You are seeing the universe as it was. The light from the Andromeda galaxy that touches your eye tonight left that galaxy 2.5 million years ago. The light from the most distant galaxies we can image left them billions of years ago. And those galaxies may not even exist anymore in the form we see them. They have had billions of years to evolve, merge, or change. The observable universe is, in a real sense, a time machine. The farther you look, the earlier in cosmic history you are seeing. The CMB, our outermost visual horizon, shows us what the universe looked like 13.8 billion years ago, just 380,000 years after it began. We are not looking at the universe. We are looking at its history, layer by layer, as each shell of light finally arrives after its long journey through an expanding cosmos. And what lies beyond? Beyond the CMB, beyond our horizon, beyond the 46.5 billion light years that define the edge of what we can observe. What is out there? That is the question we will turn to next. Let's ask a question that feels simple but turns out to be one of the most disorienting in all of cosmology. Where's the center of the universe? It seems like a reasonable thing to ask. Everything we experience in everyday life has a center. A room has a center. A city has a center. A galaxy has a center. The Milky Way has a dense, violent core roughly 26,000 light years from where we sit. Even the observable universe, as we defined in the previous act, has a center of sorts, us, by definition, since it is a sphere drawn around a point of observation. But the universe itself, the whole thing, not just the part we can see, does not appear to have a center. And the reason why is one of the most profound insights in the history of human thought. To understand it, we need to go back to the early 20th century and to a man named Edwin Hubble. In the 1920s, Hubble made two discoveries that permanently changed our understanding of the cosmos. First, he demonstrated that many of the fuzzy, cloud-like objects visible through telescopes, called nebulae, were not clouds of gas inside the Milky Way, but entire separate galaxies millions of light years away. The universe, it turned out, was incomparably larger than anyone had imagined. The Milky Way was not the whole cosmos. It was one island among billions. Second, Hubble observed something even more startling. He found that almost every galaxy he measured was moving away from us. Not just a few, almost all of them. And the farther away a galaxy was, the faster it was receding. This relationship, distant proportional to recession speed, is now known as Hubble's law. The immediate, intuitive reaction to this is, we must be at the center. Everything is moving away from us. Therefore, we must be at the middle of some great explosion, some cosmic expansion radiating outward from our position. But this intuition is wrong. And the reason it is wrong is beautiful. Imagine a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. There is no special raisin at the center of the expansion. No raisin can look around and declare itself the origin point. From the perspective of any single raisin, all the others appear to be receding. And the farther away a raisin is, the faster it seems to move away, because there is more dough expanding between them. This is not a perfect analogy. No analogy for space-time is. But it captures the essential point. The universe is not expanding into something with a center and an edge. Space itself is expanding. Every point in space is moving away from every other point. And therefore, every point in space is, in an equally valid sense, the center of the expansion. This idea that there is no preferred location in the universe, no special point that is more central than any other, is formalized in cosmology as a cosmological principle. It states that on the largest scales, the universe is homogeneous, the same in every location and isotropic, the same in every direction. No observer, no matter where they are in the cosmos, occupies a privileged position. This is one of the foundational assumptions of modern cosmology, and the evidence for it at the largest scales is strong. When astronomers map the distribution of galaxies across the sky, they find filaments and voids and clusters, structure everywhere, on scales up to hundreds of millions of light years. But zoom out far enough, to scales of several billion light years and beyond, and the distribution becomes remarkably smooth and uniform. The cosmic web looks roughly the same in every direction, from any vantage point we can calculate. There is a philosophical tradition, running from Copernicus through Galileo through Darwin to Hubble, sometimes called the Copernican principle, the principle of mediocrity. If you prefer a starker name, it is a repeated discovery that we are not special. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of anything. And we, sitting on this pale blue in the outer suburbs of an average spiral galaxy, are not observing the cosmos from any privileged vantage point. What the Copernican principle strips away in specialness, it returns in something more valuable: universality. The laws of physics we measure here, gravity, electromagnetism, quantum mechanics, appear to be the same laws operating in the most distant galaxies we can observe. The elements we find on Earth are the same elements found in stars billions of light years away. The universe is, as best we can tell, a coherent whole, governed by a single set of rules everywhere and always. There is no center. Or, more precisely, everywhere is a center which amounts to the same thing. But now let's think about this a bit more carefully, because the statement, "there is no center," has a hidden assumption baked into it. It assumes the universe is either infinite or it is finite but has no boundary, like the surface of a sphere, which has no edge and no center point on its surface, even though it is finite in area. If the universe is infinite, if space goes on forever in all directions, then of course there is no center. An infinite space cannot have a center, just as a set of all integers has no middle number. But what if the universe is finite? What if space curves back on itself, the way the surface of the Earth does? On the Earth's surface, you can travel in any direction and never reach an edge, but the surface is still finite. Could the universe be like that? This brings us directly to Act 4, the question of the edge. But before we leave the question of the center entirely, let's sit with something for a moment. The fact that there is no center, the fact that the universe has no origin point, no special location, no cosmic axis around which everything revolves, is not just a scientific conclusion. It is, in a quiet way, a philosophical statement about the nature of existence. For most of human history, the universe was imagined as a place built around us. The stars moved around the Earth. The heavens were arranged for our observation. Even after Copernicus moved the Earth from the center of the solar system, there was still a tendency to imagine the solar system as central to the galaxy, or the galaxy as central to the cosmos. Science has progressively, patiently, and without sentiment dismantled every one of these assumptions. And what remains is something stranger and arguably more magnificent. A universe with no center is a universe in which no location is more privileged than any other. A universe in which the view from a rocky planet orbiting an average star is, in principle, as valid a perspective on the whole as any other view from anywhere else. The cosmos does not have a throne room. It has no vantage point from which all things are visible. It simply is, equally, everywhere in all directions. That is not emptiness. That is an extraordinary kind of equity built into the structure of reality itself. Now, if there is no center, is there an edge? This is a question that has occupied philosophers and physicists alike for centuries, and it remains, even today, genuinely unresolved. Not unresolved in a way that some scientific questions are temporarily unresolved, where we are close and just need more data. Unresolved in a deeper sense. The answer may be, in principle, unknowable from where we stand. Let's be precise about what we're asking. We already established that the observable universe has a boundary, the cosmological horizon, roughly 46.5 billion light-years away in every direction. That boundary is real, but it is not a physical edge. It is an information horizon. It is a limit of what we can see, not the limit of what exists. Beyond our horizon, there is almost certainly more universe, more space, more matter, more galaxies. The question is not whether anything exists beyond our horizon. The question is whether space itself has an end. Does space stop somewhere? Is there a place where you could stand at the very last point of existence, where there is space here, and then nothing, not empty space, but genuinely nothing, no space at all, just beyond your outstretched hand? There are three possibilities, and they correspond to three possible geometries for the universe as a whole. The first possibility is that the universe is positively curved, like the surface of a sphere, but in 3 dimensions rather than 2. In this case, if you travel far enough in any direction, you would eventually return to your starting point, the way an airplane circling the Earth does. A positively curved universe will be finite in volume, but have no edge. You could never reach the end of it, because it has no end. It simply loops back on itself. However, it would contain a finite amount of space. This geometry is called a closed universe. The second possibility is that the universe is negatively curved like a saddle or a sheet of hyperbolic geometry. In this case, space extends infinitely outward, and parallel lines gradually diverge rather than converge. A negatively curved universe will be infinite in extent. This is called an open universe. The third possibility is that the universe is flat, that space follows the rules of ordinary Euclidean geometry, the geometry you learned in school, where parallel lines stay parallel forever, and the angles of a triangle add up to exactly 180 degrees. A flat universe could be either infinite or, in some specific topological models, finite but without boundary. The mathematics allows both. So which is it? The most precise measurements we have, from the Planck satellite's 2018 observations, combined with independent baryon acoustic oscillation data, indicate that the universe is flat, with a margin of error of approximately 0.4% at 95% confidence. It is worth noting that the Planck CMB data alone, without that combination, showed a slight preference for a closed universe. The flatness result depends on the joint analysis. The geometry of the observable universe, as far as we can measure, is consistent with flat Euclidean space to very high precision. This result is significant, but it comes with an important caveat. The measurements we make are measurements of the observable universe. The sphere 93 billion light years across that we discussed earlier, the entire universe, if it is vastly larger than our observable portion, could have a very slight overall curvature that we simply cannot detect within our limited observational window. If you were an ant on the surface of a very large sphere, the local surface would look flat to you, because the curvature would be too gradual to measure on the scale of your observations. In other words, the flatness measurement tells us that if the universe is curved, the radius of that curvature is enormous, far larger than the observable universe. But it does not tell us definitively that the universe is geometrically flat to infinite precision. Now, based on the available data, what can we actually say about the size of the universe beyond our horizon? Current theoretical estimates suggest that the entire universe, assuming the flatness result is accurate and inflation happened as current models describe, is at least 250 times larger than the observable universe in every dimension. This comes from limits on the minimum size of the universe inferred from the Planck CMB data. Some theoretical estimates place it much larger than that, potentially many orders of magnitude larger. But it is important to say clearly, we do not know the size of the universe beyond our horizon. Any specific number is an extrapolation from models, not a direct measurement. What we can say with confidence is this: if the universe is flat and if it extends significantly beyond our cosmological horizon, both of which current evidence supports, then it is, for practical purposes, extraordinarily large compared to what we can see, and it may well be infinite. But here, we must be careful again, because the word infinite in physics carries a specific meaning, and applying it carelessly leads to confusion. An infinite universe does not mean a universe of infinite density or infinite energy. It means a universe in which space extends without limit, in which there is always more space beyond any point you choose. The matter within that space would still be distributed at finite density, the same average density we measure in the observable universe. An infinite universe would simply be an infinite repetition, on the largest scales, of roughly the same large-scale structure we observe here, the cosmic web extending forever, with no edge, no boundary, no wall. And this brings us to a question that sounds metaphysical, but is actually scientific. If the universe is infinite, then by pure probability, somewhere out there, far, far beyond our horizon, there should exist regions of space that are, by chance, arranged almost identically to our own observable universe. If space extends infinitely and matter is distributed throughout it, then every possible arrangement of matter, including one that resembles our observable universe, should occur infinitely many times, simply by the statistics of infinite repetition. This is not a multiverse theory. This is a straightforward consequence of probability in infinite space. It is sometimes called a level 1 multiverse by cosmologists like Max Tegmark, though calling it a multiverse can be misleading. It is simply the far reaches of the same universe, beyond our horizon, where chance produces similar arrangements. We will discuss more exotic multiverse ideas, ones that posit genuinely separate universes with potentially different physical laws, in Part 3. But this simpler case is worth understanding on its own terms. An infinite universe is one in which our observable patch is not unique in any meaningful sense. It is simply the region we happen to be able to see. Now, what about the edge? The honest answer is, we don't know if there is one. If the universe is infinite, there is no edge. Space continues forever. The question, what is beyond the edge, has no answer, because there is no edge to be beyond. If the universe is finite, closed, curving back on itself, then again, there is no edge in conventional sense. There is a finite volume of space, but no boundary, no wall, no place where space simply ends. You could travel forever and never reach a terminus. The only scenario in which there will be something like a conventional edge, a place where space genuinely stops, would require a universe with a specific kind of non-trivial topology that current evidence does not particularly support. So the answer to is there an edge appears to be on our best current understanding. Probably not in any conventional sense. But there's a subtler point lurking here that is worth naming. Even if the universe has no edge, there is still a boundary to what any observer can ever know. The cosmological horizon is not just an edge to what we currently observe. It is, in a very deep sense, a permanent epistemological wall. As the universe continues to expand and that expansion accelerates, driven by dark energy, the most distant galaxies we can currently see will eventually recede beyond our horizon. The universe we can observe will, over trillions of years, gradually shrink. Galaxies that are today barely within our observational reach will one day slip permanently out of it, their light redshifted to undetectability in the very far future. Time scales so vast they are difficult to even write in ordinary numbers. The night sky of some future civilization, if one exists, might show nothing but our own local group of galaxies. The rest of the universe would have retreated beyond the horizon, invisible and undetectable. That future civilization, if it did not inherit our current data, might reasonably conclude that the universe contained only a handful of galaxies. This is not a distant theoretical concern. It is a reminder that what we can know about the universe is bounded not just by our technology, but by time and the physics of expansion itself. We live in what may be a cosmologically privileged moment. Early enough that the evidence of the larger universe is still visible to us, that the receding galaxies have not yet vanished beyond the horizon of the accelerating expansion. And it raises a question that sits at the intersection of science and philosophy. Is there a meaningful difference between something that exists beyond our horizon and something that does not exist at all? If no observation can ever, even in principle, detect it, that is not a question science can fully answer. It is a question about the relationship between existence and observability, between reality and knowledge. Different physicists answer it differently, and that disagreement is not a failure. It is a sign that we are at the frontier, which brings us to what lies beyond, not just beyond our horizon, but potentially beyond our universe altogether. We have established the observable universe. that sphere of 93 billion light years across, which contains everything we can, even in principle, detect. We have explored its structure, its scale, its contents. We have asked where its center is, and found that the answer dissolves the question. We have asked whether it has an edge, and found that the honest answer is probably not, and certainly not one we can ever reach or observe. But now we need to make a distinction that is crucial, and that popular discussions of cosmology frequently blur. There is a difference between what lies beyond our observational horizon and what people mean when they talk about other universes. These are not the same thing, and conflating them leads to confusion about what is established science and what is speculation. Let's deal with the first case, the simpler, less exotic, but still staggering case. Right now, beyond our cosmological horizon, there is almost certainly more of the same universe. More space, more matter, more galaxies, more stars. The observable universe is not the whole universe. It is the portion of the universe from which light has had time to reach us. The rest of the universe, the part beyond our horizon, is not a different universe. It is not separated from us by a wall, or a void, or some metaphysical boundary. It is simply space that we cannot see, because the light from it has not yet arrived, or because the expansion of space has carried it beyond the reach of any signal we could ever receive. Think of it this way. Imagine you're standing in a large, dark field at night, holding a lantern. The lantern illuminates a sphere of space around you. Beyond the edge of that light, the field continues. You cannot see it, but it is there. The darkness is not emptiness. It is simply the limit of your light. Our cosmological horizon is that edge of the lantern's glow. What is out there beyond the horizon? Current cosmological models, based on the observed flatness of the universe and the physics of cosmic inflation, the period of extraordinarily rapid expansion in the universe's first fraction of a second, suggests that the total universe extends enormously beyond what we can observe. The numbers here are uncertain and model-dependent, but they are worth considering. Based on the Planck satellite's 2018 measurements of the cosmic microwave background, physicists have derived lower bounds on the size of the total universe. If the universe is flat to the precision we have measured, it must be at least on the order of 250 times larger than the observable universe in radius, meaning its volume would be at least 250 cubed, or roughly 15 million times greater than the observable volume. And that is a minimum estimate derived from the observational limit of our measurements. The actual size could be far, far larger. Some inflation models, depending on the specific model of inflation you adopt, predict that the universe is so much larger than our observable patch that the numbers become essentially meaningless in human terms. Figures like 10 to the power of 10 to the power of 23 light years have been discussed in the literature. These are not statements you should take as facts. They are outputs of specific theoretical models, and the models themselves are not confirmed. But they illustrate a point. If inflation happened, even in its most conservative forms, the universe is almost incomprehensibly larger than what we observe. Why does inflation predict this? Inflation, first proposed by physicist Alan Guth in 1981 and subsequently developed by Andre Linde, Paul Steinhardt, and others, is the hypothesis that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Space expanded by an enormous factor in an extraordinarily short time, something like a factor of 10 to the power of 26 or more, in approximately 10 to the minus 32 seconds. Inflation was proposed to solve several problems with the standard Big Bang model. Why is the universe so uniform in temperature across regions that, by ordinary expansion, could never have been in causal contact with each other? Inflation answers this. They were in causal contact before inflation stretched them apart. Why is the universe so flat? Inflation answers this. Any initial curvature would have been stretched away to imperceptibility, the same way the surface of a balloon looks flatter as you inflate it. And as a consequence of the stretching, the universe beyond our horizon is almost certainly vast, vast beyond any intuitive grasp. Even if it is all the same universe, governed by the same physical laws, made of the same kinds of matter and energy as what we observe, there is something worth pausing on here. We spend a great deal of time, as a species, thinking about the scale of human civilization, the scope of history, the extent of geography, the reach of our technology. 12,000 years of agriculture, recorded history stretching back 5 or 6,000 years. Space probes have traveled, in 50 years of operation, perhaps 20 or 22 billion miles from Earth, which sounds impressive until you realize that 22 billion miles is about 0.000004 light years, and the observable universe has a radius of 46.5 billion light years. Our most distant human-made object has traveled approximately 1/10 billionth of the observable universe's radius. Every human life, every civilization, every war and empire and cathedral and symphony, all of it has occurred within that 1/10 billionth of a fraction of the observable universe. And the observable universe is itself, as we have established, an almost certainly tiny fraction of the whole. This is not meant to inspire despair. It is meant to inspire a particular quality of attention, the kind of attention that comes from recognizing the scale of what you are part of. Because there is another way to read these numbers. Every atom in your body was forged in the nuclear furnaces of stars. The carbon in your cells, the calcium in your bones, the iron in your blood. These were made in stellar interiors and scattered across space when those stars died. You are not separate from the universe. You are a part of it that has, through billions of years of cosmic and biological evolution, become capable of contemplating itself. The universe, through you, is looking at itself. And even from this small vantage point, this unremarkable planet in the outskirts of an average galaxy, we have measured the shape of space, traced the history of the cosmos back to its first moments, mapped the large-scale structure of the observable universe, and deduced that what lies beyond our horizon is immeasurably vast. That is not a small thing. That is, by any measure, extraordinary. Now we arrive at the question that, for many people, is the most compelling and the most mysterious. The question of other universes. Before we go any further, I want to be explicit about something, because this is a topic where the line between science and speculation is genuinely important and genuinely easy to blur. Everything we have discussed so far, the size of the observable universe, the expansion of space, the cosmic microwave background, dark matter, dark energy, the flatness of the universe, the structure of the cosmic web. These are conclusions supported by direct observational evidence, confirmed by multiple independent methods, and accepted by the overwhelming consensus of the scientific community. They are as solid as science gets. What we are about to discuss is different. The ideas in this section are scientific hypotheses, meaning they are grounded in mathematics and physics, proposed by serious professional scientists and taken seriously within the scientific community. But they are not confirmed. They are not directly observed. In most cases, they are not currently testable with any instrument we possess or can envision building. They may turn out to be correct. They may turn out to be wrong. Or they may turn out to be the kind of idea that is simply outside the reach of empirical science as we practice it. I will tell you what the hypotheses are, who propose them, and what the arguments for and against them are. But I will not tell you which one is true, because we don't know, and anyone who tells you otherwise is overstating what science has established. With that said, let's explore. The first hypothesis is the one we briefly touched on at the end of Act 4, the simplest and least exotic of the multiverse ideas. It is sometimes called a level 1 multiverse, a term used by the cosmologist and physicist Max Tegmark in his taxonomy of multiverse theories. The level 1 multiverse is not really a multiverse in the dramatic sense. It simply refers to the regions of space beyond our cosmological horizon, regions that are part of the same universe, governed by the same physical laws, but which we can never observe because the expansion of space has carried them permanently beyond our reach. If the universe is infinite, or even just enormously larger than our observable patch, then by the statistics of infinite or near-infinite repetition, there should exist, somewhere in that vast space, regions arranged almost identically to our own observable universe. Same physical laws, same types of matter, possibly even arrangement of atoms that replicate. Somewhere, conditions similar to those on Earth. This follows not from any exotic theory, but from basic probability applied to large numbers. This is philosophically interesting, but it is worth being clear. It does not tell us much we can act on. These regions, if they exist, are permanently beyond our horizon. We cannot detect them. We cannot communicate with them. Their existence is a logical consequence of certain assumptions. Principally that the universe is infinite and that matter is distributed throughout it at roughly the same average density we observe. But those assumptions, while supported by current data, are not proven beyond doubt. The second hypothesis is more radical, and it emerges from the physics of inflation itself. Recall that inflation, the rapid exponential expansion of the early universe, is strongly supported by evidence, particularly by the observed uniformity of the CMB and by the specific pattern of tiny temperature fluctuations within it. But inflation as a physical process is not a single, uniquely defined theory. There are many possible models of inflation, depending on the specific properties of the hypothetical field that drove it. In a significant class of inflationary models, inflation does not simply happen once, uniformly, and then stop. Instead, quantum fluctuations in the inflating field cause some regions of space to stop inflating while others continue. The regions that stop inflating become what we would call universes, expanding, cooling, developing matter and structure. The regions that continue inflating keep generating new stopping points, new pockets of non-inflating space, each of which becomes its own universe. And this process in these models never ends. It is self-perpetuating. It is called eternal inflation. Eternal inflation was first described by Paul Steinhardt in 1983, with Alexander Vilenkin independently developing the same idea around the same time. Andre Linde, working independently, developed a closely related model he called chaotic inflation, which also predicts eternal self-reproduction of inflationary regions. In these models, the universe we observe is one bubble in infinite, ever-expanding foam of bubble universes, each bubble having formed where a region of inflating space transitioned to a non-inflating state. Each bubble could, in principle, have different physical properties, different values of fundamental constants, different laws of physics, depending on the details of how the transition happened. This is eternal inflation hypothesis. It is a genuine scientific hypothesis, not a fringe idea. It is taken seriously by many physicists. But it is important to understand what the current state of the science actually is. There is a significant problem with eternal inflation as a scientific theory. It is extraordinarily difficult to test. The other bubble universes, if they exist, are, by the nature of the model, separated from us by regions of still inflating space, which expands faster than light. No signal of any kind can travel from one bubble to another through the inflating space between them. In principle, if two bubbles had once collided in the early history of the universe, the collision might have left a detectable imprint on the CMB, a circular anomaly, a subtle bruise in the microwave sky. Searches for such signatures have been conducted. To date, no confirmed detection has been made. Furthermore, in 2023, a study published by physicists including Ghazal Gheshjani and others demonstrated that under certain conditions, eternal inflation based on purely random quantum fluctuations leads to space-time filled with singularities, a result that, if correct, would make the standard picture of eternal inflation generating a stable multiverse of bubble universes significantly more complicated, or potentially non-viable in its simplest form. The authors of that study concluded that eternal inflation producing a stable multiverse remains, in their words, still very much an open question that will require much deeper investigation. This is not a dismissal of the idea. It is science doing what science does, scrutinizing, testing, refining, and being honest about what remains unresolved. The third major multiverse hypothesis comes from a completely different direction: quantum mechanics. Quantum mechanics, the physics of the very small of particles and fields, is the most precisely tested theory in the history of science. Its predictions have been confirmed to extraordinary levels of accuracy, but it has, since its founding in the 1920s, been accompanied by a deep interpretational puzzle. What does the mathematics of quantum mechanics actually mean? When quantum mechanics describes a particle, say an electron, it assigns the particle a wave function, a mathematical object that describes a superposition of multiple possible states simultaneously. The electron is not in one place. It is, in some meaningful sense, in many places at once. It is in a superposition. But when you measure the electron, you find it in one specific place. The wave function appears to collapse. The superposition resolves into a single outcome. Why? How? What happens during measurement? This is called a measurement problem, and it has never been fully resolved. There are multiple competing interpretations of quantum mechanics, all of which reproduce the same experimental predictions, but differ radically in what they say about the underlying reality. One of those interpretations was proposed by physicist Hugh Everett III in 1957. It is now commonly called the many worlds interpretation, though Everett himself called it the relative state formulation. Everett's proposal was this: the wave function never collapses. Instead, every quantum event that has multiple possible outcomes causes the universe to branch, to split into separate branches, one for each possible outcome. In one branch, the electron is measured here. In another branch, it is measured there. Both outcomes occur. Both branches are equally real. They simply cannot interact with each other after the branching event. In this interpretation, every quantum event, and quantum events are happening continuously at every scale, everywhere in the universe, causes an endless branching of reality. The number of branches would be unimaginably vast, growing at every instant. Each branch is, effectively, a separate universe, though all branches together constitute a single mathematical structure, the universal wave function. The many worlds interpretation is not fringe physics. It is one of the most actively discussed interpretations of quantum mechanics among professional physicists and philosophers of physics. Some prominent physicists regard it as the most natural and mathematically clean reading of quantum theory. Others regard it as profligate, unnecessary multiplication of entities beyond what the evidence requires. There is no consensus. And crucially, like eternal inflation, the many worlds interpretation does not currently make predictions that differ from standard quantum mechanics in any experimentally accessible way. The other branches, if they exist, are by construction inaccessible to any measurement in our branch. This is what makes an interpretation rather than a distinct theory. It reproduces all the same predictions, but says something different about what is really happening. There is a fourth strand worth mentioning, though we will not dwell on it as long. String theory, the theoretical framework that attempts to unify quantum mechanics and general relativity by proposing that the fundamental constituent of nature are not point particles, but tiny, vibrating strings of energy, predicts the existence of an enormous number of possible configurations of the universe. These configurations, called the string landscape, correspond to different possible values of physical constants, different strengths of gravity, different masses for fundamental particles, different values of the cosmological constant that drives dark energy. The number of configurations in the string landscape is estimated to be on the order of 10 to the power of 500. Each configuration corresponds to a different possible universe, a different set of physical laws, combined with eternal inflation, which will explore different regions of the string landscape in different bubble universes. This is sometimes called a string landscape multiverse. The string landscape idea is controversial even within string theory itself. Some string theorists view it as an important and potentially predictive framework. Others, including some who work on string theory, consider it problematic development, a sign that the theory may not be as predictive as a fundamental theory of physics should be. The physicist Lee Smolin has argued against it on these grounds. Others, like Leonard Susskind, have embraced it. This is an active and unresolved debate within the field. What should we make of all of this? There are a few things worth saying clearly. First, the multiverse is not a single theory. It is a family of distinct hypotheses arising from different physical frameworks with different characters, different predictions, and different levels of theoretical development. Treating them as one thing leads to confusion. Second, none of these hypotheses is currently confirmed by direct observational evidence. The existence of other universes, whether bubble universes from eternal inflation, branches from quantum mechanics, or configurations from the string landscape, has not been detected. Indirect evidence has been sought, particularly in the CMB, and has not been found at any agreed-upon level of significance. Third, this does not mean these ideas are pseudoscience or fantasy. They are genuine scientific hypotheses, grounded in well-established physics, proposed and debated by serious researchers. The question of whether they are testable, whether they make predictions that could, even in principle, be checked against observation, is one of the most important ongoing debates in the philosophy and methodology of physics. Fourth, the honest answer to do other universes exist is we don't know. We have hypotheses. We have mathematical frameworks. We have arguments for and arguments against. We do not have evidence sufficient to confirm or rule out any of the major proposals. And we should be humble about that. Not because the questions are unimportant, but precisely because they are so important that they deserve the honesty of uncertainty rather than the false comfort of premature conclusion. Let's come back to Earth for a moment. Literally, you are here, on a rocky planet, third from a medium-sized star, in the outer arm of a spiral galaxy, which is one of 2 trillion in the observable universe, which is itself a sphere 93 billion light-years across, which is almost certainly a small fraction of the total extent of space, which may or may not have an edge, which arose from a Big Bang 13.8 billion years ago from conditions we do not fully understand, and which is expanding, accelerating, and carrying all of its contents further and further, a part driven by a form of energy we cannot identify. This is what we know. And then there is what we don't know. We don't know what dark matter is. We know it exists. Its gravitational effects are measured, consistent, and reproducible. Without dark matter, the rotation curves of galaxies don't work. Without dark matter, the large-scale structure of the cosmic web doesn't form correctly. Without dark matter, gravitational lensing around galaxy clusters doesn't add up. Something is there, something with mass and gravity. But after decades of searching, in underground detectors, at particle accelerators, in space-based observatories, we have not directly detected a dark matter particle. We have strong evidence for the phenomenon. We have no confirmed explanation for the substance. We don't know what dark energy is. We know it is causing the expansion of the universe to accelerate. We know it constitutes approximately 68% of the total energy content of the universe. We can describe its effects with considerable mathematical precision using what is called the cosmological constant, a term Einstein originally introduced, famously abandoned, and which was resurrected when the accelerating expansion was discovered in 1998. But what dark energy actually is, physically, whether it is a property of empty space itself, whether it is a dynamic field that changes over time, whether it is something else entirely, we do not know. We don't know exactly what happened in the first moments after the Big Bang. We can trace the history of the universe back to about 1 second after the Big Bang with high confidence, and further back to fractions of a second with reasonable confidence. But the very first instant, the Planck epoch, the first 10 to the minus 43 seconds, is a regime where both general relativity and quantum mechanics apply simultaneously, and where we do not have a working theory that combines them. We do not have a theory of quantum gravity. String theory is a candidate. Loop quantum gravity is another candidate. There are others. None is confirmed. And without quantum gravity, the first instant of the universe is, in the deepest sense, beyond our current theoretical reach. We don't know whether the universe had a beginning in any conventional sense. The Big Bang marks the earliest moment our models can describe, but the models themselves break down at that point. The question of what, if anything, came before the Big Bang, or whether before, even has meaning in that context, since time itself may have emerged with space at or near the Big Bang, is genuinely open. There are cosmological models, like the conformal cyclic cosmology of Roger Penrose, or various bounce cosmologies, in which the Big Bang was not a beginning but a transition from a previous state. These are serious scientific proposals. They are also unconfirmed. We don't know the ultimate fate of the universe with certainty. The most likely scenario, given current measurements of dark energy, is something called the Big Freeze or heat death, a future in which the universe continues to expand indefinitely. Stars burn out, black holes evaporate over unimaginable timescales through a process called Hawking radiation, and the universe approaches a state of maximum entropy, cold, dark, diffuse, and essentially structureless. But this assumes dark energy remains constant, that the cosmological constant is truly constant. If dark energy grows stronger over time, some models predict a different end. The Big Rip, in which the accelerating expansion eventually overcomes not just gravity, but the electromagnetic and nuclear forces, tearing apart galaxies, then solar systems, then planets, then atoms themselves. If dark energy weakens or reverses, other scenarios become possible. Current data cannot yet distinguish between these possibilities with certainty. We don't know whether we are alone. This is perhaps the most personally felt of all the open questions. The universe contains at minimum several hundred sextillion stars. A substantial fraction of those stars have planets. A substantial fraction of those planets are in the habitable zones of their stars. The chemistry of life, carbon, hydrogen, oxygen, nitrogen, the basic organic molecules, appears to be widespread, found in interstellar clouds, in meteorites, in the atmospheres of distant worlds. And yet we have, so far, no confirmed detection of life beyond Earth. Not a signal, not a fossil, not a microbe. The question of whether life and intelligence exists elsewhere in the universe is one of the most profound open questions in all of science. The absence of evidence is not evidence of absence, as the saying goes, but the silence is real. Here is what I want to leave you with. We began this journey at home, on the surface of a rotating planet, embedded in the motion of a cosmos we didn't choose and didn't design. We traveled outward through scales that defy intuition, past billions of galaxies, to the edge of what we can observe, and then further still into the territory of what we can only hypothesize. And at every step, the honest answer to the deepest questions was, we don't fully know, but notice what we do have. We have measurements. We have the precise temperature of the cosmic microwave background, accurate to a fraction of a degree. We have the orbital dynamics of thousands of exoplanets. We have the spectrum of light from galaxies so distant their photons left before the Earth existed. We have mapped the large-scale structure of the observable universe across billions of light years. We have detected gravitational waves, ripples in space-time itself, from black holes colliding a billion light years away. We have, in the last few years alone, with the James Webb Space Telescope, seen galaxies forming in the first few 100 million years after Big Bang, farther back in cosmic history than any instrument before could reach. This is not a small thing. This is a young species, barely 100,000 years old on a 4.5 billion year old planet, that has figured out, using mathematics and light and ingenuity, the age of the universe, the shape of space, and the composition of stars 100 billion light years away, using nothing but photons that happen to cross our path and the capacity to reason about them. There's a version of cosmology that feels humiliating. In this version, the universe is so large and we are so small that the logical response is insignificance. What difference does any of it make? What could we possibly matter in a universe of 2 trillion galaxies? But I don't think that version captures what the science actually says. The universe is large. We are small. Both of these things are true. But the universe is also, as best we can tell, unconscious. It does not wonder at itself. It does not ask questions. It does not sit up at night and try to understand the CMB, or calculate the distance to Andromeda, or debate the merits of eternal inflation. As far as we know, and we should be humble about this too, because we don't know what we don't know, the act of comprehension of one part of the universe constructing a model of the whole is rare, possibly extraordinarily rare. You are a part of the universe that has learned to ask where it ends. That is not nothing. That is arguably one of the most remarkable things in the 13.8 billion year history of this cosmos. We don't know if there are other universes. We don't know what lies beyond our horizon. We don't know what dark energy is, or what dark matter is, or what happened in the first instant after the Big Bang. We don't know if we are alone, but we know we are asking. And we know that the asking matters, not just to us, but to the universe itself, insofar as the universe is capable of knowing anything at all. The edge of the universe, if it exists, is beyond reach. The center of the universe, if such a thing could be said to exist, is nowhere and everywhere. The universe beyond our universe, if there is such a thing, is, by definition, invisible to us. But the question endures. And as long as there are minds to ask it, minds made of carbon and water and electrical signals, minds assembled by 13 billion years of cosmic and biological history, minds that can point a telescope at the night sky and read the ancient light, the question will continue to be asked, and sometimes that is enough.